the physics breakthrough that redefined nothingness. For centuries, nothingness was considered empty, a silent backdrop where reality simply happened. But deep inside modern physics, scientists discovered something unsettling. Nothing was not empty at all. To understand why this matters today, we need to revisit one of humanity's oldest assumptions, that space is either filled with something or it is nothing. Classical physics treated emptiness as absence. No particles, no energy, no activity. But as technology allowed us to look closer, that idea began to fracture. The modern world now depends on systems so precise that even emptiness had to be measured. The first cracks appear when physicists studied the smallest scales imaginable. At quantum levels, particles did not behave like solid objects. They flickered in and out of existence. Energy appeared briefly, then vanished. Space itself seemed restless. What was supposed to be nothing behaved like something alive. At first, these effects were dismissed as mathematical artifacts, convenient equations with no physical meaning. But experiments refused to cooperate. Instruments detected fluctuations where emptiness should have been silent. Forces emerged from vacuum states. Particles appeared without cause, borrowing energy before returning it almost instantly. Then came the realization that changed everything. This restless vacuum was not a side effect. It was fundamental. Empty space contained energy, and that energy influenced the universe at every scale. Cosmic expansion accelerated. Subatomic particles gained mass. Forces behaved differently depending on the structure of nothing itself. The vacuum was no longer a stage. It was an actor. This reframed some of physics' deepest questions. If empty space contains energy, where did it come from? Why does it have the value it does? And what happens if it changes? The answers carried consequences far beyond theory. Because once nothingness became something, the stability of reality itself was no longer guaranteed. And physics was about to confront the unsettling idea that the universe rests on a foundation that is never truly still. As experiments grew more precise, the implications of an active vacuum deepened. Physicists realized that empty space was governed by fields, invisible structures stretching across the universe. These fields never shut off. Even at absolute zero, they fluctuated, vibrating with residual energy. This discovery explained anomalies that once seemed unrelated. Tiny forces pulling metal plates together in a vacuum. Particles gaining mass without any visible source. The universe expanding faster than gravity alone could explain. What linked them all was nothingness behaving like a reservoir of energy. At first, this seemed like a theoretical curiosity. Strange, but distant from daily life. Then technology caught up. Quantum devices became sensitive enough to feel vacuum fluctuations directly. Atomic clocks drifted. Sensors picked up noise with no classical origin. Engineers were forced to account for the physics of nothing just to keep systems stable. The conflict sharpened when calculations revealed a staggering mismatch. The energy predicted to exist in empty space was vastly larger than what the universe actually exhibited, off by factors so extreme they defied intuition. Physics had uncovered a problem it could not solve. If vacuum energy were even slightly higher, the universe would tear itself apart. If lower, matter might never have formed. The value appeared finely balanced, resting on a razor's edge, and no theory explained why. Some physicists proposed unseen dimensions. Others suggested entire universes canceling each other out. A few entertained the idea that reality itself selects stable configurations. None were proven. All were unsettling. What had begun as a correction to old equations became an existential puzzle. The universe existed not because nothing was empty, but because nothing was precisely tuned. And that realization carried a chilling implication. If the properties of nothingness could change, even slightly, the laws of physics might shift with it. Reality, it seemed, was balanced on the quiet behavior of nothing at all. The conflict reached its peak when physicists began asking a forbidden question. What if nothingness is unstable? What if the vacuum we inhabit is not the lowest possible state, but a temporary one? According to modern theory, empty space can exist in different configurations, each with its own energy level. Our universe may be resting in a false vacuum, a state that appears stable but is not permanent. Beneath it could lie a deeper, more stable form of nothingness, one that obeys different rules entirely. The danger was not theoretical drama. If a transition occurred, it would not arrive gradually. It would propagate at the speed of light, rewriting the laws of physics as it went. Particles would lose mass. Forces would change. Atoms might no longer hold together. There would be no warning, no survival, just a quiet reset of reality. This possibility forced physicists to confront scale in a new way. The smallest fluctuations could trigger the largest consequences. A single quantum event occurring anywhere could reshape everything. Stability was no longer guaranteed by size or age. Experiments searching for new particles and energies took on new weight. High-energy collisions were scrutinized. Cosmic events were monitored, not because scientists expected catastrophe, but because understanding the vacuum became essential to understanding existence itself. At the same time, vacuum energy offered promise. If harnessed, it could revolutionize energy production. The universe contained an ocean of latent power hidden in empty space, but accessing it safely remained beyond reach. The risks were as profound as the rewards. This was the heart of the conflict. Nothingness was both the source of cosmic stability and a potential point of failure. The same vacuum that allowed stars and life to exist also held the theoretical power to undo them. Physics had revealed a universe not anchored by solid foundations, but suspended by a delicate balance of invisible energy. And for the first time, humanity understood that even nothingness carries responsibility. The realization landed with quiet weight. Nothingness was no longer a void to ignore. It was the most fundamental structure of reality itself. Every particle, every force, every moment existed because empty space behaved exactly as it did. Physics did not uncover this truth to inspire fear, but humility. The universe was not built on certainty. It was balanced on conditions so precise that even the slightest change could unravel everything. Stability was not guaranteed by permanence, but by balance. In practical terms, this understanding reshaped science. Models of the universe were rewritten. New theories emerged not to conquer nothingness, but to coexist with it intellectually. The goal shifted from domination to comprehension, from control to respect. For the public, the change was subtle. Life went on. The sky did not fall. But beneath everyday experience sat a profound insight. Reality is not solid beneath our feet. It is negotiated moment by moment by forces we cannot see. Nothingness, once dismissed as absence, turned out to be the quiet architect of everything. It shapes galaxies. It governs time. It holds the universe together without ever being visible. And perhaps that is the most unsettling lesson of all. The most powerful forces are not always loud or obvious. Sometimes they're defined by what we cannot touch, measure, or even fully understand. So what do you think? Are we standing on solid ground or balancing on something far more fragile than we ever imagined?